Today our topic is electrochemistry. A lot of portions from electrochemistry is removed by NCRT for this year. So we will not discuss that topics here. We will discuss it later after reopening of our school. Electrochemistry. Last year in the chapter redox reactions, we discussed the basic concepts in electrochemistry. Electrochemistry deals with electrolysis and galvanic cells. Electrolysis is a very useful method which can be used for electroplating and for the purification of metals in metallurgy and the electroplating. The electrolysis is very important. And galvanic cell, as you know, now in cars, solar for the storage of solar electricity, we are using storage cells. So Daniel cell in the laboratory, we are using Daniel cell, and nickel cadmium cell, lithium cell. All these are familiar to you. All these are galvanic cells, and in space programs, fuel cells are used. So electrochemistry, that is very much related to our life, and it has a lot of importance in our life. Here in the first part, we have to study Nernst equation, but before studying Nernst equation, you have to remember what is a galvanic cell. A galvanic cell is a device which converts chemical energy into electrical energy. That is a galvanic cell. Last year we discussed zinc copper cell. You may remember it. You can see the figure of zinc copper cell. Here zinc electrode oxidation takes place, so therefore we can call it as anode. Anode in which oxidation takes place. So zinc, what is the cell? The anode reaction is then gives 2 electrons plus, then 2 plus. So electrons will be released here, and that electrons will pass through this external circuit. That electrons will pass through this external circuit and will reach here in the copper electrode. Here it will combine with the Cu2 plus in the electrolyte and forms copper metal. So that is a zinc copper cell. It is also known as Daniel cell. Here you can see a salt bridge. What is the function of salt bridge? In order to maintain the flow of electricity or to maintain the continuity of electrolyte solutions, we are using the salt bridge. Cell reaction, electrode reactions, electrode potential, cell potential, measurement of single electrode potential. All these things we discussed last year, and you have to refer the notes and textbook to understand these topics clearly. And do you remember the equation to find out the standard cell potential? Standard cell potential E0 cell is equal to E0 of cathode minus E0 of anode. Here, in a Daniel cell, if you apply an external potential, what is happening? That we will discuss here. If you are applying an external potential which is less than 1.1 volt, external potential is less than 1.1 volt, then the process will be as in the case of Daniel cell. That means zinc will undergo oxidation, copper will undergo reduction, electron from zinc will move towards copper through the external circuit. So current flow from copper to zinc. Here it is described very clearly. Electron flow from zinc rod to copper. Zinc dissolves at anode and copper deposits at cathode. That will take place. If the external potential is less than 1.1 volt. And now two more cases. Which are the two more cases? Can you say? External potential is equal to 1.1 volt. That is one case. And the next case? Yes, external potential greater than 1.1 volt. These two more cases are remaining. You can see if it is equal to 1.1 volt, what happens? No flow of current or no flow of electron from zinc to copper. It will be in an equilibrium condition. No flow of electrons or current, no chemical reaction. Now we can go to the third case where the external potential is greater than 1.1 volt. In such a case, the opposite cell reaction will take place. That means copper will undergo oxidation and electrons will flow from copper to zinc, and Zn2 plus will be reduced to zinc metal. Electrons flow from copper to zinc and current flows from zinc to copper. Zinc is deposited at the zinc electrode and copper dissolves at copper electrode. It will take place. So this year you have to study Nernst equation to calculate electrode potential and Nernst equation to calculate cell potential. Nernst showed that for the electrode reaction, Mn plus an electron gives M. It is a reduction reaction. Mn plus means a metal ion in the N plus oxidation state. When it accepts N electron, what happens? It will change it to metal. Mn plus an electron gives M. The electrode potential at any concentration measured with respect to standard hydroelectrode can be represented by. Directly we are going to Nernst equation. There is no derivation of Nernst equation. Directly going to Nernst equation. We are not going to derive it. If the cell reaction is Mn plus an electron gives M, then Nernst equation Mn plus bar M. Mn plus bar M, that is equal to E0 Mn plus bar M, standard electrode potential, minus RT by NF Ln, natural logarithm, concentration of M divided by concentration of Mn plus, that means concentration of product divided by concentration of reactant. But here M is in the solid state. It is clear from this equation. So its concentration will be constant. So we can rewrite the equation as Mn plus bar M is equal to E0 Mn plus bar M minus RT by NF Ln 1 by concentration of Mn plus. So electrode potential, you know what is electrode potential? Last year we discussed it. Faraday constant 96,500 coulombs, or accurately 96,487 coulombs per mole. It is Nernst equation for electrode potential. We can derive Nernst equation for cell potential by taking the example of Daniel's cell. Daniel's cell is zinc copper cell. And in zinc copper cell, the cathode is copper electrode and anode is zinc electrode. First, we can write Nernst equation for copper electrode. ECU2 plus bar Cu is equal to E0 of Cu2 plus bar Cu minus RT by 2 of Ln 1 by Cu2 plus. 1 by Cu2 plus. And similarly for the anode, Zn2 plus bar Zn is equal to E0 Zn2 plus bar Zn minus RT by NF Ln 1 by Zn2 plus. So the cell potential is cell is equal to E of copper minus E of zinc, cathode minus anode. E0 of Cu2 plus bar Cu minus RT by 2F Ln 1 by Cu2 plus aqueous minus E0 of Zn2 plus bar Zn plus RT by 2F Ln 1 by Zn2 plus. So here E0 Cu2 plus bar Cu minus E0 Zn2 plus bar Zn, that is E0 of cell, minus RT by 2, we can take it as a common RT by 2F, Ln Zn2 plus concentration of Zn2 plus by concentration of Cu2 plus. And when we convert the natural logarithm to the base 10, what happens? 2.303 RT by 2F log concentration Zn2 plus by concentration of Cu2 plus. So here you can see the equation E cell is equal to E0 cell minus 0.059 by 2. And how you listen here, instead of RT 2.303 RT by F, 0.059 is given. How will you get 0.059? By substituting the values of R, F and T, but T is taken as 298 Kelvin. So at 298 Kelvin, if your calculations are at room temperature, that is at 298 Kelvin, then you can use this equation. E cell is equal to E0 cell minus 0.059 by 2, 0.059 by 2 log concentration is Zn2 plus by Cu2 plus. So we can generalize this equation for any reaction. Suppose the cell reaction is AA plus BB gives CC plus DD. Then next equation is E cell is equal to E0 cell minus 2.303 RT by NF log concentration of C raised to C into concentration of D raised to D divided by concentration of A raised to A into concentration of B raised to B. Here C and D are the products, A and B are the reactants, small c, small d, small a, small b are the stoichiometric coefficients in the balanced cell reaction. Some problems based on this you can see. It is not based on Nernst equation. It is simply to calculate standard cell potential. The first cell is 2Cr plus 3CD2 plus gives 2Cr3 plus 3CD. That is a cell reaction. From the cell reaction, it is clear chromium is oxidized to Cr3 plus. So that is the anode. CD2 plus is reduced to CD. That is the cathode. So what will be the equation to find out cell potential? E0 of cell is equal to E0 cathode minus E0 anode. So here cadmium is the cathode, so E0 CD2 plus bar CD minus E0 Cr3 plus bar Cr. Now substitute the values. E0 of CD2 plus bar CD minus 0.403 minus 0.74 is equal to 0.337. That is the answer. Similarly, in the second case, Fe2 plus bar Ag plus gives Fe3 plus Ag. Fe2 plus is oxidized to Fe3 plus, that is the anode. Ag plus is reduced to Ag, that is the cathode. Our equation is E0 cathode minus E0 anode, E0 of Ag plus bar Ag minus E0 of Fe3 plus bar Fe2 plus. Substitute the value 0.80 minus 0.77 is equal to 0.03. Another question based on Nernst equation. Write Nernst equation and EMF of the following cells at 298 Kelvin. The first one is Mg bar Mg2 plus in bracket concentration 0.001 molar. Double bar Cu2 plus concentration 0.0001 molar bar Cu. So here we can write the cell reaction first. Here it is asked. Write the Nernst equation and you have to calculate the EMF. If you want to write the Nernst equation, you have to write cell reaction first. What is the cell reaction? Mg plus U2 plus gives Mg2 plus Cu. Now Nernst equation. Based on this equation, you can write Nernst equation. What is Nernst equation? E cell is equal to E0 of CO2 plus bar CO minus E0 of Mg2 plus bar Mg minus 2.303 RT by NF log. Concentration of Mg2 plus divided by concentration of CO2 plus. Substitute the values. Copper 0.34 minus E0 of magnesium minus 2.37 minus the temperature is 298 for 0.0591 divided by 2 electrons. 2 moles of electrons are involved, therefore N is equal to 2 divided by 2 log concentration of Mg2 plus 0.001 concentration of C2 plus 0.0001 and calculate it, you will get the value as 2.0005 volt. Similarly, you can solve the second one, and I will give you some assignments also, and I think we can stop it here, and you have to solve the assignments and submit it in time.